My name is Milad BenRahuma from National Oil Corporation of Libya. My talk is titled Sedimentary Facies Development and Stratigraphic Architecture of the Early Devonian Sediments in Western Libya. First of all, I have to thank the National Oil Corporation for giving me the permission for participation in this conference and supporting me financially. Also, my special thanks goes to Petroleum Research Center for providing me the necessary data for this study when I was working with the Petroleum Research Center. Also, special thanks goes to my first professor, John Prost, from University of Rennes1 and CNRS in France. My special thanks goes also for my second professor, Remy Ishar from IFP, and now he is working with Total Oil Company. Also, I am very grateful to Saadun Murad from Uppsala University for supporting me and supervising the petrographic part of this study. This study is a small part from my PhD studies, which is carried on during 2010. Outlines, I would like to start with why this study, and then I will go to objectives of this study, then sedimentological study and facies association, and construction of the depositional model. After that, we have to see outcrop sections correlation and compiled generalized section, then correlation of local relative sea level change with the global one, and then outcrop subsurface correlation, petrographic study, and finally we end with conclusion. Why this study? Because of an overall lack of knowledge of Devonian times, environments in Libya and its consequences on oil exploration and production, location and origin for source rocks and reservoirs. This chart showing the oil in place distribution in Gdams Basin, where we can see that the early Devonian sediments consist about 35 of oil in place, comparing with the other ages. So we can have idea about the value, the importance of the early Devonian of in Gdams Basin. Objectives, we have to go through sedimentological study of the early Devonian sequence, both in the field and the subsurface, correlation of the outcrop sequence with the subsurface sequences of Gdams Basin. And in order to understand the controls of deposition, we have to compare the relative sea level change of the study area with the global relative sea level change. The study area located in the southern flank of Gdams Basin, where Gdams Basin is located in the western part of Libya. It's bounded from the south by El Gargaf Arch and from the north by Nafusa al-Dahar Arch, from the east by Tibesti Tripoli Arch, and it's extend into Algeria western part. The area of study is located in the southern flank of Gdams Basin. Here, this red rectangular here. This one. This is the outcrop area. About 6 sedimentological studies were studies in details in the outcrop area. Stratigraphy of the early Devonian succession. The early Devonian succession in Western Libya started with Luscovian and extend into Emzian. In the subsurface of Gdams Basin, The Luscovian, the early Devonian sediments represented by Tadrak Formation and Wankasa Formation. Tadrak Formation in the subsurface started in Luscovian time and extend into the early Emsian, which is overlain by Wankasa Formation, and Wankasa Formation extend into the early Aphelian time. In the outcrop area, Tadrak Formation is dated Bragian, while Wankasa Formation is dated Emsian. And Tadrak is directly rests on the Silurian, very limited sediments of Silurian and Momoniad Formation, where the Luscovian and the upper Ordovician is missing in the outcrop area of southern Gdamis Basin. Further in the south, we have the early Devonian sediments is completely missing, where we have the Aphelian sediments, Awanatunin A. It's directly rests on the Cambro-Ordovician rock. So there is a big hiatus in the southern flank of Gargaf Arch. Facies association, we have about 8 to 10 facies association described from the outcrop studied area. Facies association one is consists of medium to coarse grain sandstone displaying finding upward grain size, which is started with large scale cross bedding. These cross bedding is overlie the Caledonian unconformity here, and the cross bedding showing finding upward grain size. It's developed into a smaller scale cross bedded, which is interpreted as a fluvial sediments. Facies association 2 is composed of fine to medium grain sandstones. It's exposed unidirectional cross bedded with high concentration of mud clasts along the lower plane boundaries of beds and along also the reactivation surfaces, which is interpreted as intertidal environment. Facies association 3 consists of fine to medium grained and conformably overlie shale, which is recognized as a channel. This channel deposits consist of scoletus and diplocraterium. Usually at the top we have a ripple or wave marks, which is interpreted as a subtidal channel. Facies association 4, it consists of fine grained sandstone, highly bioturbated, and consists horizontal bioturbation, usually, or sometimes we can find some algal mat associated with these sediments, which is interpreted as semi-restricted subtidal environment. Facies association 5, which is consists of fine grained sandstone, display coarsening upward or shallowing upward, dominated by wave ripples and mud, a lot of mud clasts concentrated along the reactivation surfaces with some scoletes. This facies interpreted as upper shore face. Facies association 6, which is consists of alternations of fine grained sandstone with very fine grained sandstone. The very fine grained sandstone usually display wave ripples with scolete stress fossils. The fine grained sandstone consists of diplocraterium and scoletes with some horizontal furrows and display horizontal bedding planes or horizontal bedding. This facies association interpreted as upper to lower shore face. Facies association 7 is consists of alternations of shale and very fine sandstone and siltstone with some homoky cross stratification. Consists a lot of bioturbation with some fossils and shell fragments interpreted as upper offshore environment. Facies association 8 is dominated by shale and consists sometimes homoky cross stratification with some fossils interpreted as lower offshore sediments, which is considered as the distal depositional setting in the studied sections. There is another two facies association is neglected. I will not speak about in this presentation because of its similarity with the subtidal environment here, so I neglect them. This figure showing Tadrat formation dated Braggian, which is consists of medium grain sandstone displayed by directional cross bedding, probably deposited within tidal environments. This Tadrat formation directly rests on Mominiat formation, Ashkelian time. So we have Caledonian unconformity here, where we have the whole Silurian sediments is missing in this study. And we can see here there is a hard ground where we have ferruginous material concentrated along the surface or the top of Mominiat formation. So this is a Caledonian unconformity, which is correlated during the whole of the northern Gondwana land and considered as a regional unconformity. In this locality, we have about 33 million years is missing. So this is considered as a type 2 sequence boundary. Few kilometers toward northwest, we found the Tadrat formation directly rests on about 15 meters thick of Tanizift formation. So in the study area, we have only 15 meters thick of Tanizift formation, which is scattered in some areas. These sediments of Tadrat formation consists or composed of coarse, medium to coarse grained with large trough cross bedded and a lot of reactivation during or these reactivation associated with some gravels interpreted as a fluvial sediments. The overlying sediment, we have unidirectional cross bedding associated with convolute structures. These convolute structures consist of concentric layers around highly calcareous core with some mud clusters concentrated along the reactivation surface or the bedding planes, and some wave ripples, some current ripples described from the top of the beds. These probably deposited within subtidal environment. Sometimes these sediments alternated with bidirectional cross bedding, which is a typical herringbone structure indicating of tidal influence. Above, we recognized wave ripples, fine grained sandstone, which is considered as a major transgressive or considerable transgressive surface, separating the low stand system tract from the transgressive system tract. At the top of these beds, we can see some current ripples. Sometimes we have wave ripples. Above, we can see here tidal channels, alternations of tidal channels with the spring and neap tidal bundles, alternated with ripple sand flat. The ripple sand flat consists of fine grain with the current ripples, sometimes with wave ripples, and it's alternated with tidal channels. We can see the spring tide and neap tide bundles, which is indicate the influence of tide processes in this upper part of Tadrat formation. Again, multiple reactivation of channeled systems. So we have alternations or superimposed channeled systems during the upper part of Tadrat formation. We can see there is a lot of tidal channeled system characterize the upper part of Tadrat formation, and these sediments consists of fine grain, which is dominant in the upper part formation, indicate that the upper part is dominated by tidal processes. This is a panorama figure showing that the Tadrat formation consists in its lower part fluvial dominated, and in the middle part is tidally influenced, and the upper part is tide dominated, which is considered or interpreted as an estuarine depositional system proposed for the Tadrar formation, and the sequence boundary and the sequence, a depositional sequence 1. This is the uppermost beds of Tadrar formation, which is consist of fine-grained sandstone. These fine-grained sandstone, dominated by wave ripples, contain of diplocraterian and tigellite or scolitus. This is considered as shore face environment. It's overlain by fine to very fine sandstone, wave rippled, and then we have light gray shale deposits, which is indicate that we have upper shore face and then middle to lower shore face and upper offshore here in the uppermost part. This is the termination sandstone beds. It's the final termination beds of Tadrar formation and the uppermost part of first transgressive surface. The shale here is belong to Wankasa formation, and it's considered as the beginning of Tadrar Wankasa formation. These shale units can be correlated with the Emsian flooding surface, which can be correlated along the whole study area in the outcrop and the subsurface surface, on the subsurface area. These shales is suddenly interrupted with erosional surface, which is consist intraformational clasts and considered as the second sequence boundary here, which is terminate the first sequence, the positional sequence. And of course, it's mean that we don't have the high stand of system tract, or the high stand systems tract is missing in this area of study. The second depositional sequence is about only 7 meters thick. It's started with fine grained sandstone, highly biturbated, overlain by fine grained sandstone with wave ripples, interpreted as upper shore face, change it upward into middle shore face. And then we have shales alternated with very fine sandstones and siltstones, interpreted as offshore. These offshore sediments or shelly offshore sediments suddenly overlain by coarse-grained sandstone with current ripples and sigmoidal facies, interpreted as upper shore face. This sudden change in grain size and environment considered as a sequence boundary here, separating the second depositional sequence from the third depositional sequence. The third depositional sequence is started with fine to medium grain sandstone, sigmoidal shape, and consists a lot of mud clasts concentrated along their activation surfaces. And then we can see the bundles or tidal bundles. This is the need bundles and spring bundles, which is indicate of tidal channel depositional environment. These sediments overlain by fine grained sandstone. These fine grained sandstone consist of placer bedding in the lower part, which is overlain by bidirectional cross stratification, and then we have wave bedding interpreted as a sand flat here or sand environments. Reactivation of tidal channels is clearly observed in the upper part here, where we can see here a lot of channel tidal channels. The upper part of Wankasa Formation is started with medium-grained sandstone. These medium-grained sandstone showing sigmoidal shaped depositional sequences, which is probably indicate of lateral accretion of subtidal environment. Here, above we have superimposed parasequences or coarsening upward or shallowing upward parasequences. These parasequences consist at the top sometimes wave or current ripples, which is indicate of prograded shore face environment. This prograded shore face environment developed upward into lower and middle shore face, and then the upper part is fine grained, very fine-grained sandstone with wave ripples, consists a lot of trace fossils. The uppermost bed of Tadrat Formation composed of fine-grained sandstone. These sandstones usually expose wave ripples and sometimes hummocky cross stratification interpreted as lower to middle shore face environment. This bed is unconformably overlie the offshore sediments here. And at the top, we have a ferruginous crust at the top, which is indicate a small hiatus or small time of non-deposition. This bed is terminate or the final or the uppermost bed of Wankasa Formation. This bed overlain by light gray shale deposited in offshore environment, which is interpreted as a maximum flooding surface and terminate the transgressive surface of the third depositional sequence. This shale is correlated with the early aphelian sediments, which is belong to the Middle Devonian, and it's not included in this presentation, and correlated in the subsurface with the Mgayit shale, which is considered as a hydrocarbon seal for the underlying reservoirs of the early Devonian. So the stacking pattern of Wankasa Formation is interpreted as a tide influence delta of Wankasa Formation. The outcrops are correlated to each other. So we have the first depositional sequence is consists of low stand system tract and the transgressive system tract. The transgressive system tract is interrupted by unconformity intraformational, which is consist intraformational clusters. This so we have the high stand system tract is missing in the first depositional sequence, and the second depositional sequence is only 7 meters thick, and the low stand and high stand system tract is missing. The third depositional sequence is the low stand is missing, and the high stand system tract is belong to the Middle Devonian sediments. This is a generalized section for the lower Devonian, which is produced from the correlation of these sections. There is a relative sea level change proposed for the studied sediments. These relative sea level correlated with with the sea level curve proposed by Johnson et al. 1985. So the conversion of our local relative sea level with Johnson relative sea level, we can see a lot of maximum flooding surfaces can be correlated with Johnson 1. And this is the Caledonian unconformity at the base of Bragian here. Also, it can be correlated with the global event of Walliser 2008, I think, 1996. So we can see very clear Zelikov event and Deligi event, Shotek event can be also or can be clearly observed in our stratigraphic section in the early Devonian sediments. Yes, this is the correlation of the outcrop area with the subsurface wells. The base of early Devonian is the Caledonian unconformity, which is make angular unconformity with the underlying Silurian sediments. And it's started with Luscovian sediments in the northwest of Gdam's Basin, and it's missing in the southern part of Gdam's Basin and in the outcrop. The estuarine, the positional setting of the upper Tadrart formation, it can be correlated in the whole area in the outcrop and the subsurface. The lower Tadrart, the lower Wankasa formation of tidally influenced sediments can be correlated with the carbonate rocks in the northwestern part of Gdam's Basin, and the upper part of Wankasa formation showing deepening and thickening basinward, which is transferred to the basin with very deep depositional setting. The uppermost bed of Wankasa formation can be correlated through the whole area in the outcrop and Gdam's Basin, and this is the maximum flooding surface overlie the third or overlie the transgressive system tract of the third depositional sequence, which is correlated with the embayed shale and making the hydrocarbon seal for the underlying reservoirs. Petrographic study, we can see here monocrystalline quartz grain, and in the porosity between the grains, we can see kaolinite clay mineral. This is a close view of the kaolinite, and we can see a lot of porosity or microporosity within the crystals of the kaolinite. This slide showing a decayed clay minerals filling the pore space with some hematite minerals or oxide minerals. This is a close view of the outlined area here. This is a monocrystalline quartz with chloride clay mineral filling the pore spaces between the grains. This is a close view from another location showing the chloride clay minerals. This slide showing ferruginous or iron oxide mineral, which is completely obliterating or mostly obliterated the pore spaces within the quartz grains. And we can see some remnant porosity, which is indicated by the blue, light blue color here. This is a close view of ferruginous material, which is surrounding the quartz grains and attacking or attack the quartz overgrowth around the grains. This is a monocrystalline quartz grain with the quartz overgrowth around the quartz grains. So we can see a lot of quartz overgrowth, which is developed during the mesogenesis diagenetic event. This is very fine sandstone and very fine sandstone and coarse silt, which is consists a lot of porosity or diagenetic porosity or secondary porosity. This is a botoroidally and arranged iron oxide and oxyhydroxide that engulf quartz overgrowth, indicating telogenesis origin or telogenetic diagenetic event. This is a close view taken by scattered image microscope, which is showing the same phenomena of iron oxide cementation. In conclusion, this figure showing if rock fabric average distribution by age of the studied sandstone, where we can see the detrital grains, cement material, porosity, matrix, and clay distribution by age. So we can see that the Braggian and Emsian sediments consist about 21% or 20 to 21% of porosity, which is considered as very good porosity. This figure shows the rock fabric average distribution by system tract, where we can see the low stand system tract consists very high porosity, which is reaching about 38% of porosity, and gives a very important value for the low stand system tract as a reservoir for hydrocarbon. In conclusion, about 10 or 8 to 10 siliciclastic facies association were identified, ranging from fluvial to lower offshore depositional environment, deposited within 3/3 order depositional sequences. The depositional sequence exhibited low stand system tract dominated by fluvial character, often tidally influenced. The transgressive system tracts are tidally or tide and shore face. The lower offshore and to lower offshore composition and the high stand are missing or very limited in the outcrop and more obvious in the subsurface. The early Devonian succession exposed in our Natonin area is smoothly correlated to the subsurface of Ghadam's Basin, where it's revealed deepening facies basinward. Subsurface stratigraphic correlation revealed higher amount of sediments came from the south and southeast, with minor source from the north. The early Devonian sediments represent very important reservoir properties, which sealed at the top by Mugayit or Ephalian maximum flooding surface of offshore shale of Mugayit shale correlates with the lower shale unit of Awanatunin 1 formation in the outcrop area of Awanatunin. These reservoirs are sometimes overlie the early Silurian source rocks, particularly in the southern area of Ghadam's Basin, which facilitate hydrocarbon exploration with minimal risk. The proposed relative sea level change of the study area expose clear analogous manner trend with the works of Johnson et al. 1985, which clearly indicate that the studied succession essentially controlled by the globally static sea level change. Thank you very much.